Hello, welcome to Nested High School Computer Science. I'm Sam. Let's get started. Today, we're talking sorting algorithms. Then we'll go on to selection sort. So, a few notes about sorting algorithms. Obviously, these algorithms are meant to sort things. And like most algorithms in computer science, they can work differently. So what do you need for these algorithms to work? Well, you need a way to say, given two items, which item comes before the other item. And this can be based on their value, if they're numbers or alphabetical order, or the size of some value. This can be applied to any type of item. You just need to choose on which property of an item you're sorting on. So say if you're sorting people, you might want to sort by their age. We also like to keep two key metrics when talking about sorting algorithms, and these are the number of comparisons and the number of swaps. I'm going to talk about selection sort now. Selection sort's one of the more easiest selection algorithms. It's rather intuitive as to how it works. So with sorting algorithms, we have this idea of a current item and the next item. So with selection sort, you have we'll call it a pointer to your current item, and you also have another pointer that is moving through the list. In selection sort, you move through the list, you find the next smallest item, and you swap it with your current. And then you just move your current item forward to the next one, and then you repeat this process. So you are continually selecting the next smallest item, thereby building up a sorted list that goes from smallest to largest. With these sorting algorithms, we're going to do little demos. These demos come from a website called sortingalgorithms.com. The link will be in the description. So this is sortingalgorithms.com. This website presents a series of sorting algorithms and shows you data in a random order, a nearly sorted order, a reversed order, and a few that are unique. We're going to run the random order. As the algorithm runs, you can see the red pointer find the next smallest item. Once it's found the smallest item, it'll replace it with the current item pointer, which is not shown. As you watch this animation, you can almost tell where the next smallest is, and you can almost beat the algorithm in your own head. Now you can see it's starting to speed up quite fast towards the end. Let's take a look at some nearly sorted data. As you can see, the algorithm doesn't adapt to nearly sorted data. It'll take just as long. For every item in the list, it'll check every other item to find the next smallest. The algorithm still doesn't improve on a reverse list or a list that has a few unique items. So that was a demo of selection sort. What did we see? We saw that for every item in the list, the algorithm had to check with every other item as to what the next smallest was. So we get this for every item concept, which is a classic telltale sign of an O(n) squared algorithm. So the number of comparisons is equal to the number of items square. A good thing about selection sort is it does do the minimal number of swaps. So if your cost of swapping data is high, this is the algorithm to use. However, selection sort does not adapt to the data. We saw with a reverse list, or a nearly sorted list, or a few unique list, the algorithm carried out the same number of steps as any type of random data. We saw the algorithm get quicker as it moved through a smaller list, which leads us to believe that for larger lists, this algorithm is not the one to use. Overall, selection sort isn't very useful unless the swapping operation has a large cost. This has been an introduction to sorting and selection sort. Please like and subscribe. If you have any questions, please tell me in the comments and I'll get back to you. Thanks for watching. I'll see you next time.